Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing the course Computational Aerodynamics. And in today's topic, we'll see momentum equation in differential form. Okay, so let's actually see how we derive momentum equation in differential form, and what are the role of each term in governing the fluid flow problem. So these things we will see. So here we'll be seeing how this fluid particle is moving with the flow. Okay, so this is the fluid particle which we are taking. So here you can see this is the fluid particle, so which is moving from point 1 to 2 with respect to space and time. So this x, y, z is the spatial coordinates and t is the temporal coordinate. So this fluid particle is moving from one point to other point. So this sort of approach we see it is for a moving fluid element, and we call it as a non-conservative form. And so the equations of motion when we are deriving for a fluid particle which is moving with the flow, so then we derive a non-conservative form of equation. Okay, so let's see. So what are the forces acting on this fluid particle? And so here you can see this is the fluid particle, so it has x, y, z coordinate axis. So the volume of the fluid particle is dx, dy and dz. So the volume of the fluid particle is dx, dy, dz. And you know that mass is equal to density into volume. So therefore the mass of this fluid particle will be rho into dx, dy and dz. So this is the mass of the fluid particle. Okay, and so basically this momentum equation when we are seeing, so the basic principle involved to derive momentum equation is second law of Newton. Okay, so rate of change of momentum dp by dt will be equal to f, so which is equal to d by dt of m into b. So this is what we have. Okay, so F is nothing but, so the external forces acting on the fluid particle. So it is divided into two categories. One is you have normal force and other one is tangential. Okay, so your normal force and tangential force. So in the normal, like you have pressure and normal stress. Okay, and here you have tangential shear stress. Okay, so basically this f whatever we are seeing is the surface force. So there is one more force which is the body force. Okay, so basically this normal and tangential, so this will come under surface force. Okay, so surface force in the sense it will act on these planes. So basically E, G, F, so this is one plane. Next B, C, G, F, this is one plane. So on these planes, so the force will act perpendicularly and force will act tangentially. So when it is acting perpendicularly, so you can see you have normal stress and basically you have the pressure. So these aspects. So for the body force, it is acting over the entire volume. Fine. So this is what we have. So now let's see basically how the force resolution is happening. So let us consider. So you have this cube particle. So you have 6 faces. So let us take this as phase 1 and this is phase 2. Okay. So 1 and 2 faces are, let's say it is left and right. So the area of these faces will be, so this one which is dz and this is y. Okay, so here you have dz and dy, so this is the area. Okay, so next we have 3 and 4 which is top and bottom and top, 3 and 4. Okay, so 3 and 4 basically it is bottom and top. So what is the area here? Basically here again you have dz but here you have dx. So this is what we are taking. So you can see for both the two things. So we have the area, so dz and dx. Okay. So after that, what we have? So 3 and 4 is done. So then after front and back. So we have 5 and 6. Okay. 5 and 6 are nothing but front and back. So 5 and 6 is nothing but front and back. So the area will be what? So the front plane is, you have dy and you have dx. Okay. So the area is dx dy. Okay. So when we take the fluid particle, so here this is a cube fluid particle. So on the left, you have 6 phases. Phase 1, 2, 3, 4, 5, 6. So 1 and 2 are left and right phases. 3 and 4 are top and bottom phases. Then after 5 and 6 are front and back phases. So for these phases, how the pressure is acting, how the normal stress is acting, how the shear stress is acting. So these things we should see. And fluid particle will move from one point to other point when there is an unbalanced force of these forces. Okay. So here you can see that. So basically what we have is, like, you can see this is the area. You can see dy dz, so dx dy. So these things are the area which we are talking. Fine. So now what do we have? So let's say force, what we are taken. So force is divided into like surface force, and this is body force. For the body force, you have gravity actually. Gravity, electromagnetic, these things. So when you take the gravity, so what is gravity? So weight, let's say, is equal to m into g bar, let's say. So g bar is nothing but a vector. So which will have component gx, gy, gz. Okay. So gx, gy, gz. And what is mass? Mass is equal to density into volume. So density into dx, dy, dz. Okay. So dx, dy, dz is the volume. Fine. So this is what we have for the weight. Now, basically, what will be the body force? Like W is equal to rho into dx, dy, dz into g bar. So this is what we have. So let's say if you are taking for body force along x-axis, then you will have gx. If you take body force along y-axis, you will have gy. If you take body force along z-axis, then you have gz. So that is the difference that we have. Okay. So we are done with the body force, and we have seen what are the surface forces. So pressure and shear. Now let us take the plane B, C, G and F. Okay. And consider A, next D, H and E. So we have two planes. So let's take this plane. So what do we have? B, C, G and F. Okay. So you have other plane here. So what do we have? A, D, H, E. So you can see the pressure will act perpendicular to the surface. So it is acting. So pressure P is acting towards the positive x direction. So P, and if you want pressure force, then into area. So what is area? dy into dz. Okay. Similarly, so when this fluid particle has the distance of dx in this way, so the change in pressure on the other face will be, so that would be P plus dou P by dou x into dx into area dy dz. Okay. So you can see that here the left hand side, so which is left hand side, which is 2 and which is 1, we have taken. So where if the pressure P is acting, so on the right hand side, so there is an additional pressure or a decrement pressure. If there is the same pressure, then there is no net force acting on the fluid particle. It will remain rest. Okay. So this unbalanced pressure is like, so we had seen, So what is the variation of pressure with respect to x distance and into this area? Okay, so the net force would be, so what we have, so since the pressure uh, in the left hand side is acting positive direction, we will write P into dy dz minus, so this is acting negative direction, so P plus dou P by dou x into dx into dy dz. So what happens here? This term will get cancelled. Okay, so the remaining term would be minus dou P by dou x into dx dy dz. So this term, so minus dou P by dou x into dx dy dz, so is the pressure force, net pressure force, which is acting on the fluid particle along x direction. Okay, so when we see the faces, these things like the left and right faces, so there is an unbalanced pressure here on the right face, and it is acting along the negative y-axis. So that's why you have face, let's say this is 2 minus 1. So basically this is the net pressure that we are getting, and you got like minus dou p by dou x into dx dy dz. So this is what we have. Okay, so next the same concept. So we had seen along x direction, so you have minus dou p by dou x into dx dy dz. So this is the pressure which is acting net pressure which is acting along x direction. Similarly along y direction, what you have, so you can see here, similarly you will have along y direction minus dou p by dou y the dx dy dz. So this is what we have. Similarly along z direction you have minus dou p by dou z dx dy dz. So these are the net pressures. So these are the net pressure which is acting along x, y, z direction. So we are done with the pressure force. So these are the terms which we have. So after that, if you see the normal stress, okay, so this is the normal stress which is acting, and this is the normal stress which is acting. Okay, so this normal stress is acting basically in a tensile manner. So here you can see, so one normal stress along the left hand side, like right hand side, is acting towards positive x-axis, and other one towards the negative x-axis. So the net one would be tau of xx plus dou tau of xx divided by dou x into dx into dy dz minus tau of xx dy dz. So this is the net. Normal stress which is acting along x direction. So here you can see this one and this one will get cancelled, and the net normal stress which is acting along x direction would be tau of xx. So dou tau of dou xx into dx dy dz. So this is along x direction. Similarly along y direction you have tau of yy into, like, divided by dy into dx dy dz. So this is along x, this is along y. Similarly along z direction you will have zz divided by dz into dx dy dz. So this is what we have. So basically in the previous instant we had seen what is the net pressure which is acting along x, y and z direction, and now we have seen what is the net normal stress that is acting along x, y and z direction. Okay, so if you see here, basically this is what we had seen. So the net force which is acting along x direction is nothing but P minus, so this is what we have. So this is the normal stress which we have seen. So here there are the terms which is the shear stress. Okay, so we will see what is this actually. So basically here you can see that, so this left and right are the planes which has the normal stress and the normal force acting. Okay, so perpendicular to these planes. So let's say what are the other planes? So top and bottom and front and back. So these are the planes where you have the shear stress. Okay, so top and bottom, front and back. So you have the shear stress. Okay, so basically what is happening on the top? So what is the top plane actually we are seeing? So top plane would be Z and X. Okay, so this is the X and this is the Z. Okay, so therefore, so top or bottom, whatever we take. So here you can see, so you have tau of Zx. Okay, so next you have tau of Zx and this direction. Okay, so let's say on the top surface, let's say you have one shear stress which is acting along the Zx plane, so along this negative x direction, and on the bottom surface you have tau of Zx plus tau of Zx divided by dou x dou z into dz, so which is acting on the bottom surface. So what would be the net here? So you have tau of Zx plus dou tau of Zx divided by dou z into dz into dx and dy. So this is what we have, and minus tau of Zx into dx dy. So this is what we have. So basically, if you see the net term, so this term and this term will get cancelled. So the net term would be dou tau of Zx divided by dou z into dx dy dz. So this is the net shear stress which is acting along the zx plane actually. Okay, so zx plane. Similarly, the net shear stress which is acting along xy plane. So what do we have? You can guess from here itself. So what do you have? Tau dou tau of let's say yx divided by dou y into dx dy dz. Okay, so this is what we have, the net shear stress which is acting along x direction. Okay, sorry, net shear stress which is acting along the zx plane and along the yx plane. Okay, so we had seen the net pressure force, net normal stress, and body force, and then we had seen what is the net no, shear stress. Okay, so we have done with external forces which are acting on the body. So we had seen completely. So when the F external force is splitting into surface and body forces, the surface force is divided, like surface force are like pressure and normal stress, and we had seen the net components along x direction. Then you have body force, which is nothing but W is equal to m into g, so which is nothing but rho into dx dy dz into g bar. So this is what we have for the body force. So then after this thing, like you have m in, like you have d by dt of m into v. So this is what we have. So F external is equal to d by dt of m into v. Okay, so here we had seen the left hand side is nothing but external forces. So on the right hand side, so it is the acceleration of the fluid particle, so which we are interested. So if you see UV rule, let's say dm by dt into v plus v into plus m into dp by dt. Okay, this is what we have. So basically, what dm by dt will be 0 when mass is constant, and here m into dv by dt. So this dv by dt is nothing but the acceleration of the fluid particle. So this will be equal to F external forces. Okay, okay. So which is acting on the fluid part m into dv by dt. So this is the acceleration of the fluid particle. Okay. So we are done with the forces and we are done with the acceleration. So basically here in the previous classes we have seen the acceleration of the fluid particle, which is dv by dt, is nothing but you have the local derivative dou by dou t plus v dot delta. Okay, so here the acceleration of this fluid particle will be split into two quantities. So one thing is nothing but the fluid particle which is moving with the space. So you have the local derivative, and here when it is moving from point 1 to 2, okay. So with respect to space, so when it is moving, so what is the acceleration inward? So that has to be taken into account. Then after, so you have dou by dou t, which is nothing but the local. So at this particular point or at this particular time, so what is the fluid particle? So what is the acceleration of this fluid particle? So we need to calculate it. And then after you have v dot delta, which is nothing but the convective derivative. So due to the movement of fluid particle from point 1 to 2, so what is the acceleration inward? Okay, so these things we need to see. Okay, so here you can see basically the net force which is acting along x direction. So you have minus dou p by dou x. So you have dou tau of x by x. So these things which we have. Okay, so into dx dy dz, and the body force you have this rho is nothing but density. So this is the acceleration on x direction. So dx, dy, and dz. So here, if you see basically for the momentum equation, so ax is nothing but acceleration along the x direction for the fluid particle. So which is nothing but du by dt. Okay, so we had seen in the previous slide. So F is equal to m into a. So how did we get F? So rate of change of momentum. So P is equal to m into v. Okay, so dp by dt will be equal to d by dt of m into v. Okay, so here if you take the acceleration, sorry, if you take the mass as constant, so then what happens? M into dv by dt. So which is nothing but m into a. Okay, so this a acceleration vector is of three components. So you have ax, ay, and az. Okay, since we are dealing with the x momentum equation, so you have m into ax. Okay, so this is what we have. So here the equation terms which we have is nothing but the pressure. So here you have the normal stress. Here these two are the shear stress or the tangential stress, and here you have the body force. Okay, so basically these two, whatever the terms which we have 1 and 2, are the normal forces which are acting on the fluid particle, and these two, the other terms, are nothing but the shear stress, and here this term is nothing but the body force. Okay, so here this dou u du by dt. So when we have seen this du by dt is nothing but what? We can expand this one as, so this is substantial derivative or the total derivative. So we can write it as dou by dou t, dou u by dou t plus v dot del into u. Okay, so this is the expansion form of this du by dt. Okay, so basically what is v dot delta? What is v dot delta? So basically v is nothing but u of I cap plus v of j cap plus w of k cap. Okay, so delta is nothing but dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. So this is what we have. So one is the divergent, other one is the velocity. So when you have v dot delta, so then you have the dot product of two vectors. So where we can see it now. So basically dot product like v dot delta is nothing but u into dou by dou x plus v into dou by dou y plus w into dou by dou z. Okay, so this is what we have. Okay, so this term is nothing but you have the convective acceleration for the fluid particle when it is moving from point 1 to 2. So the acceleration involved during the motion of this fluid particle. Okay, so then after we have the other term which is dou by dou t. is nothing but so at this particular time instance, so what is the at a particular time instance, so what is the acceleration involved? So this is what we will be seeing. So for the local and the convective acceleration. So why we are learning this? Because so here you have the total or the material derivative. So this term will be splitted into, so let's say this dou u by dou t term is there. So it will be splitted into by dou t plus v dot delta into u. So this is what we have. Next, dou v by dou t is equal to, so dou v by dou t plus v dot delta into small v, which we have. Next, dou w by dou t, which will be equal to, so dou w by dou t plus v dot delta into w. So basically these terms, so you have the x momentum, which is nothing but acceleration along x. So here acceleration along y. So here acceleration along z direction. Okay. So here you don't have dx, dy, dz term. Why? Because see, this rho is coming from mass, which is nothing but density into volume. So this volume is nothing but rho into dx, dy, dz. So on the left hand side and the right hand side, you have common terms of dx, dy, dz. So left hand side and right hand side, it got cancelled. So that's why you have rho into dou u by, like du by dt. So the equation, whatever you are seeing here, these are derived for per unit volume. Okay. So these equations, so whatever we have derived is for the per unit volume. Why? Because dx, dy, dz are common for left hand side and for right hand side. So in the previous diagram which we have, so we have derived it for, so this thing. So we had seen the momentum equation, so which we have derived it for along x direction. So we had taken along x direction what is the normal and what is the tangential force and what is the normal stress that is acting on the fluid particle, and this F external forces which are acting on the fluid particle. So we had seen the net forces. Then after m into a, so we had taken the acceleration along x-axis. So this acceleration along x-axis, you have m into du by dt. So this du by dt is split into like the local derivative and substantial derivative. So this is the full form of the Navier-Stokes equation, which is derived in the differential form. And this motion of this fluid particle from 1 to 2, since it is moving, so the equations which we have derived is non-conservative form. So the same concept is applied along y direction and along z direction. So along y direction, what we have? So we have rho into dv by dt, same things. And here, if you observe the difference, so dou p by dou x. So this is the pressure gradient which is acting along x direction. So if the fluid particle wants to move along x direction, you should have this pressure gradient. And similarly, if fluid particle has to move along y direction, you should have this pressure gradient along y direction. Okay. So then after you have the normal stress, so which is acting on the surface, so which is along this left and right plane, so tau of xx. Similarly, along y-axis you have tau of yy. Okay. So here for the shear stress you have xy and you have zy, and here you have the body force along y direction. Okay, you have body force along x-axis, you have body force along z-axis. Okay, if you observe this diagram for the fluid particle, so since gravity is acting along negative y direction, so let's say this gravity is acting along negative direction. So this only, so here fx will be equal to 0, fz will be equal to 0, so fy will be equal to minus fy actually. So if you take gravity into components, different components, so the gravity along x direction will not be there, and along z direction will not be there. So along negative y direction will be there. So then you have only these terms. Okay. So now if you see, like we had this normal force and then after normal stress, so shear stresses. Okay. The same thing. So what we have is like the density, and then after you have the acceleration of the fluid particle along z-axis, and here the pressure gradient. So if the fluid particle have to move along z-axis. So you should have the pressure gradient along z-axis. So similarly, you have this normal stress, dou tau of zz. Okay, so this tau of zz, this normal stress, and other shear stresses, tau of xz and tau of yz. Okay, so then after you have this body force which is acting along the fluid particle. Okay, so these three equations, so whatever we have seen, this 1 and 2 3, so let's say these three equations are called full form of Navier-Stokes equation. So these equations basically will govern the fluid motions. So if a fluid wants to move from one place to other place, so this equation will give information that unless you don't have a pressure gradient, then only the fluid can move. So let's say let us see a scenario. Okay, so let's say you have a room here. Okay, so this is inlet and this is outlet. Okay, so these are like walls. So if flow wants to go from inlet to outlet, so the pressure here, let's say this is P in, and pressure here, let's say P out. Okay, so if the pressure in is greater than P out, then flow will move from in to out. Okay, so because of the pressure difference or the pressure gradient only, the flow is going from one point to other point. If there is no pressure gradient, then the flow cannot move from one point to other point. So if the reverse scenario happens, let's say, so if P out is greater than P in, so then what happens? So here the pressure is higher actually. So what happens here? So here you will have high pressure, here you will have low pressure. So the reverse flow will happen here. Okay, so this is the scenario that we have. Similarly, so let us take an example of wind tunnel actually. So let us draw a wind tunnel here, a rough sketch of wind tunnel. Okay, so let's say this is inlet. Okay, so this is the test section, and this is the diffuser, and this is outlet. Okay, inlet, test section, diffuser, and outlet. So this is the general block diagram of the wind tunnel. So here at the exit you will have some fan. Okay, so this fan will be rotating with high RPM. So from Bernoulli's you can know that when the velocity is high, the pressure will become lower. So at the inlet you will have honeycomb sections. Okay, so here pressure P will be P atmosphere. Here pressure will be P atmosphere minus delta P. Okay, why? Because of this rotation of the fan, you will have the decrement of pressure here. Okay, so because of this decrement, then what happens? So the flow will go from inlet to outlet. Okay, so here from the continuity principle, you know that as area decreases, the velocity increases in the test section. Then after at the diffuser section, you have the divergence section. So what happens from the continuity itself? So from as area increases, the velocity decreases. So it will try to actually maximize the pressure and make equal with this exit pressure. Okay, so this is one scenario where you can apply the concept of this Navier-Stokes equation. So for the wind tunnels or any other scenarios, so if you want to propagate flow from let's say inlet to outlet, so here you have a test section. So what we are doing, we are making pressure difference actually. So let's say this is 1 and 2 and 3 and 4. So what is the pressure difference between 1 and 2 and 2 and 3 and 3 and 4 is very important. So at each and every sections, so 1 and 2, 2 and 3 and 3 and 4, so the pressure difference, so basically at 1 should be greater than 2, 2 should be greater than 3, 3 should be greater than 4. Then only flow can move from 1 to 4. If not, you will have a reverse flow scenario. Okay, so these basic examples are governed by the Navier-Stokes equations. So which is the concept to see the physics of the fluid phenomena. Okay, so this is one of the application, and basically there are numerous application of this Navier-Stokes equation. So these Navier-Stokes equations are called the momentum equation, So it is not only able to predicting the flows of air, it is predicting the flows of water, any other. So basically here the density and the tau, you have the viscosity. So based on the density and viscosity of this fluid, so you can vary. So whether it is a water or whether it is a air or glycerin, honey or blood, these aspects. So any type of flow, if you want to see the physics of the fluid, so you can use these equations. So these equations are universal to govern fluid flow phenomena. Okay. So in the next things, we will see the classification of PDE and other aspects of the grid. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.